Okay, awesome. Thank you, Ted. Yeah, so good catch. I didn't update the title slide at first, so if anyone saw that, I had the wrong title at first. So we're talking about continuous optimization. This is the final section that is kind of pure math. After this, we get a little bit into more of the like, how do we use this in the actual application of training of machine learning models? So this whole section was talking about continuous optimization. And so the whole high level idea is we have some objective function, we have a loss, we have some number, and we're trying to make this number go down. And so that objective function might be how close are you to the correct answer? That might be cross entropy, that might be many different things. And so we have that function, and then we basically say, make this better. And that can come in many different forms, but we're looking specifically at the continuous optimization setting. So we know basically that the neural networks and the other things that we'll be trying to do with this will be continuous, and we can move them around, and we can take the gradients and do various operations like that. You can have black box optimization and other things that have significantly different properties. We can't solve them in the ways that we'll be looking at. And so ideally, we'd like to find a global minimum, but in all of these systems that we're looking at in their complexity and nonlinearity and everything that's going on there, in reality, it's difficult to find a global minimum. So we'll be happy enough with local minimums, or we assume that those points are very often close. Um, so here's the diagram that they give us at the beginning of every chapter, just kind of showing the various different pieces that we'll be looking at. I won't walk us through everything. We'll just talk about it when we get to it. But this is the diagram that they give us at the beginning of every chapter. And so just looking at continuous optimization, we have this function. And so imagine we're trying to find the minimum point of this function. So if we have the whole plot, we can look at it in this plot and just say, okay, the lowest point is here when it's this meets with this blue dotted line. But if we have higher dimensional space, if we have something that's more complicated than this, it might not be so easy to just visually see. We might just have a equation, and then we have to say what is the minimum of this, or find the minimum. And so you can imagine if we were doing something that was just kind of locally probing. So say we just start at a random point. We say, okay, start with a value of 2, for example. And then we said, take the gradients and then move in the correct direction. We would go down this bowl, and then eventually we'd say, okay, well, if I go this way, it goes up. If I go that way, it goes up. And then we get stuck in this little local bowl. So this is a local minimum, and ideally, we'd like to go all the way over here. And so with simple methods, we might get stuck and just say, okay, we're done, when in reality, you didn't actually find the global minimum. Um, so there's various different techniques for optimizing. We'll be looking at gradient descent. And so if we assume that our functions are differentiable, so we design our neural networks typically to be differentiable, we take a loss function that's differentiable, like that's a set of constraints that we typically put on ourselves. There's other things that we could do, but we choose to make them differentiable. And then in that setting, we can do various things. So that lets us calculate the gradient. And the idea there is you calculate the gradient, and then you move a step in the negative direction, and then that moves you towards the minimum. And so this plot here is showing us, okay, we have this bowl, and each of these lines here is a contour line saying all of these are equal values. And then the next contour line is saying, like, this one's a little bit smaller, a little bit smaller. And so same thing as the previous plot. You don't typically have the whole thing plotted out, and you can't just point at it and say, this is the best. You'll typically have something that's in higher dimensions, or is more difficult to solve for. But using gradient descent, you can see it's taking a step, it's starting here, it's going up to this point down there, and it's kind of oscillating back and forth, and eventually it gets to a minimum point. So you're not guaranteed that this is the global minimum unless you have other constraints in place. But this is basically the idea is you take the gradients and then you say take steps in the right direction, and eventually you'll get to the correct final value. Um, and so one of the things that they were talking about in this chapter was that the speed of convergence is dependent on the condition number. So what the condition number is the ratio of the maximum to the minimum singular value. So if we think about this, if we had a space that was more elongated, then you might get more oscillation. And so this is saying that the condition number is something that kind of tells you how well it's going to behave. So if you have something that's very long and thin, and then you end up with all of this oscillation back and forth, your convergence is probably going to be slower because it's in a narrow, more difficult space. And so one of the things they mentioned is this idea of a preconditioner. And so the preconditioner is this concept of let's modify this space, transform this space in some way so that it can be more properly shaped so that you have a better condition number. So the idea is you have some preconditioner. This is a transform you can do on your space that is hopefully cheaper than just the extra convergence you gain from it. And then you can say, okay, transform it back out of that space. And if it's a simple enough space, if you could just say, okay, stretch this now so it's equal so that your condition number is one, then you have a much better behaved space. So
Right.
yeah.
If I could just make two quick comments. So if you look at the diagram you have on your slide, at the starting point in the lower left, like we can see that there's just like one global minimum in the like dark purple, right? But the gradient does not point at the bottom of the bowl. The gradient is pointing like straight downhill. And that's not even a really bad condition number, you know? That's like a whatever, 1.2 or 1.4 or something like that or whatever. So you imagine it gets even worse if it's what they talk about a long, thin valley. But the other thing is that the valley is not guaranteed to be perfectly straight forever. The valley can actually have bends and turns. And so then you can't even see what's beyond the valley that's right next to you. So this is the general problem with gradient descent, is that like, yeah, you can look at a very simple diagram like this and come up with a different formula than regular gradient descent. That'll take you straight there. But if you imagine that it's like literally, like if you just think about like mountain valleys, they're all crooked and branch and do this and that. How do you find the lowest valley floor amongst all the valleys? It's not obvious how you do that.
Yeah, good point.
Can I ask a question on the previous slide? You say that you scale by some learning rate.
Mhm.
How in principle would you compute learning rate?
So there's certain typical defaults, but that's a parameter that you have to change and find what the optimal is. So people start. Yeah, I mean it's that's a hyperparameter that's going to change how quickly it converges, what final point it's going to converge to. And so depending on the constraints of your problem, there might not be an obvious, you can't compute this is the best learning rate. So that's something that people do often, kind of just many trials. They say, okay, train 10 different models, what seems to be the optimal learning rate. Yeah. Yeah.
See analogy about the values, the values problem. Like how you find which valley is the most shallow valley. With your analogy, what if like you could shape the space, like take a finite amount of values, and then kind of like shoot an audio signal into the space and see how long it takes for each signal to come back. Is that something I guess people have tried to attempt in terms of solving this problem, instead of like doing the step by step until you reach a minimum, versus like use something that's faster than you can move, like, I don't know, like an audio sound or whatever, and seeing how long it takes for it to get back to you. Like,
Let me jump in there. There's something called ray tracing, but plane tracing for voxel graphics that does some math like that. But I don't think that applies here because we don't actually know what it looks like. If you compute everything, that's what's going on.
And you don't use, yeah, sorry, go ahead.
And a follow to that is, so let's suppose we have an 11-dimensional system. Is it possible that there's going to be more than 11 local minima?
Oh, yeah.
Could we use that? Okay.
You could have a zillion infinite minima, almost infinite number of local minima. But the thing is, if you just have an arbitrary loss function in a neural network, your idea of like shooting something out and searching, basically that takes as long as taking a step. You have to evaluate the function at that location. It's not necessarily a bad idea. There are algorithms, I don't think there are any common ones now, but where you actually will say, like, let's try 3 different directions and I'll just take a step in the one that worked the best, right? But at the end of the day, because it costs 3 times as much, are you better off just taking 1, 2, 3 steps in a row instead of doing that extra work of trying out stuff?
one brief follow up. Is that signal they use, like, could they use light? Because light actually travels every possible path and then chooses the path
But
that's.
this is not the real world. This is a loss function. We're drawing visuals to give you an intuition of it. But basically you have a function, and in this case, the loss function that we're trying to minimize, and it has a value everywhere. So if you want to shoot a beam over there, that's fine, but then you have to evaluate the function at that location. And that's the costly part.
Okay.
So you can evaluate as many places as you want before you take a step, but each of those evaluations is the expensive part.
Okay.
What the gradient is telling you is like, what's the best direction to take a step in? Because there are algorithms like MCMC, Markov chain, let's call it, where you are just randomly searching through the parameter space, but they only work for very low dimensional models because otherwise the parameter space can be just and so this is sort of a guide, I think, is how I think of it.
In that case, we know that we want to update our weights in the direction of the minimum, like, the minimum change, yeah, in the gradient, minimum change function, so it's like minus gradient.
Well, the goal is to maximize the change in the gradient. So
Yeah.
multiple is right. And to answer my own question, yeah, if you had a sine cosine function, you essentially have a ring where in the center could be the lowest point. So could everywhere outside that ring, they could all be the same lowest point.
Yeah.
So, in summary, this is just kind of like the baseline way, like all these different algorithms and attempts to solve this problem. This is kind of like this serves as like the most base model version of that. It's kind of like the idea everybody's trying to build upon in order to solve this problem.
This is the majority technique. Like when
Okay.
people train models, this is typically what they do. And there's a lot of stuff that people are researching, but this is like
The thing.
when someone says they're training a neural network, they're typically doing this. Yeah.
Cool.
Yeah, and it's not even just neural network. If you just use scikit-learn and you say, I want to do logistic regression on my tabular data, there is no closed form equation that lets you get the minimum. For linear regression, there is a closed form formula. So it is actually going to use something like gradient descent. Now, it's a slightly different, fancier version, but it's still. So there are many, many things that just don't have closed form equations. And what are you going to do? And so there's no guarantee. Gradient descent could get you to a local minimum that's terrible compared to the global minimum, but that's, again, if you assume you just don't know, it's infinite, many directions you could go, what are you going to do?
Sorry, about linear regression, I think it's more computational expensive to inverse matrices in terms of the direct solve of this equation in terms of linear regression. We of course know the equation, but the solving these equations demands us to inverse matrices, and this is very computational intensive. I think the wise thing, like the wise way to do is just to use gradient descent.
Yeah, yeah, and there's lots of issues in terms of how costly is the closed form, and then also, I'm not an expert on this, but what you'll see, the actual implementations have to deal with numerical stability. So you don't want underflow, overflow on your floating point numbers. And there's reasons why people choose certain algorithms because basically, if you're an expert, you might know it's safe, but if it's you or me and I just plug it into scikit-learn, I don't know. And so I don't know enough to say, warning, this is, you know, I might have some big numbers and small numbers that are very similar or something, you know. And so it has to just use by default the safest algorithm that will work for almost all situations.
Okay, wow, so excellent. Thank you guys. Enlightenment.
Yeah, so the next section was talking about momentum, and they had a little brief portion on that. But I think that the distill visualization and write up on it is definitely worth a read. So I'll just play with this for a second and just talk through what's actually happening. So this is similar to the previous plot, but this is something interactive. So this kind of shows two things. So it shows the learning rate and how you can adjust that, and you can see how that impacts things. So that was to your question earlier about how do you find the correct learning rate. This is something where you can visually just adjust this and see how it impacts things. But you have to think about this in terms of like if you were training a neural network, every time you're adjusting this, you have to go take 1,000 steps to go see how this runs, and it's not exactly obvious what the final result is going to be before you actually run it and see what happens. So you can adjust this learning rate. And then the other thing that they're trying to show here is the momentum. And so the momentum is this idea of if you're taking each of your steps greedily, then you're not taking any information from the previous step. So the momentum is saying basically take a moving average of your previous steps, and that can kind of inform you to more smoothly go in the correct direction. So we can adjust this learning rate here, and we can see if I go really small, then it doesn't really move anywhere. It doesn't go down this slope at all. If I go too high, it starts just going crazy and is just missing all of the steps. It's going too far. It's overshooting where it's trying to land. And then the other parameter is the momentum. So the momentum we can turn down, and then each of his steps is getting greedier and greedier. So momentum 0 is just looking at the gradient at that specific point, and momentum much higher, it's taking the knowledge from the previous step, saying, okay, this time I generally was moving in this direction. I'm going to continue moving in this direction. So even though it's oscillating over here, each step it's realizing, okay, the gradient seems to be going generally in this direction, and it kind of smooths out and realizes it needs to go in this direction. So momentum and learning rate are both very important. If you set these incorrectly, you're either wasting compute saying I'm taking a ton of little tiny steps, or if you set it way too high, then you're not going to converge. And same thing with the momentum. In practice, most people just keep the momentum at some kind of standard default, and then most people mess more with the step size, the learning rate. But momentum is very important. Like if you compare stochastic gradients descent with and without momentum, momentum helps a ton when you're actually training a neural network. So
Online version of the book.
this is from Distill. So Distill is just this group that has put together a bunch of resources explaining various different things about neural networks, training, machine learning in general. And they have a bunch of very good visualizations for like everything. So I highly recommend checking this out. It looks like they haven't published anything in a long time, but yeah. So this isn't related to the book. This is just a separate resource. So what we've been talking about mostly is batch gradient descent. So you look at all of your data, you calculate the gradient, you sum it up, and then you say, which direction should we go in? And that's okay when you have a small data set, maybe medium data set. But then when you get bigger, 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 you realize, okay, I have to calculate this forward pass or whatever you're doing a million times for each of your data points. And then you say, I have to calculate a million things before I even take a single step. And so that can be very expensive. Like if you think about the training that a lot of people have been doing with large language models right now, they talk about the number of tokens that they've processed. So some of the runs have been 18 trillion tokens at this point. If you said, I have to calculate this 18 trillion tokens, and then I'm going to take one step. You'd run for months and then you get one step and it would probably not be very good. So what people have figured out is that you want to, you can alternately do a single point at a time. And that instead of giving you the true gradient will give you just an estimate of the gradient. So you just say, what is the gradient for this individual point? And then you say, move in that direction. And it will be very noisy. So like what we were seeing on the momentum plot, you're probably moving around a whole bunch, but in general, you're moving in the correct direction. And that's another one of those areas where momentum will help you. But then people have realized, partially because of it helps you more smoothly converge, and partially because of just hardware constraints. If you say, I'm going to just calculate one point at a time, that makes you take a lot of steps, but then your steps are going to be very noisy. And we have this hardware, these GPUs that can do many in parallel. And so you said, okay, it's virtually free for me to run 64 at a time or 128 at a time or something like that. And that gives you a much better estimate of the gradient. And it's virtually free because it doesn't take extra time to calculate it, because your GPU is just saying, do all of these things in parallel. And then it gives you that better estimate of the gradient, and you can do it in virtually the same amount of time. And so one of the extra things that I wanted to add from this is there's kind of this idea of critical batch size. So there's this whole paper from OpenAI, and I won't go into detail on this, but it's generally the idea that there's a trade-off between your batch size and your convergence rate and the amount of actual time it takes. So you want your gradient to be like nicely behaved. So you want a large enough batch size that you get a good estimate, but you don't want it to be so big that you're not getting any extra marginal value to it. So if you set it to 8K, for example, you have 8,000 in your batch, and it already is giving you a very good estimate of your gradient, and then you double it to 16K, it might take you twice as long to compute, but it's not going to make you converge 2 times as fast. It doesn't mean you have to take half as many steps to get to a good result. So they have a bunch of plots in here saying basically like there's certain trade-offs and constraints that we're working within because we don't have infinite memory and we don't have infinite speed. And so given this, what is kind of our point of like increase the batch size to this amount because it helps us converge faster, but not so big that we're just wasting time taking these very, very big, slow steps. So if anyone wants to dig into that paper, that's a good paper for understanding how you scale batch size and how that impacts how quickly you converge and how much time it will take you to train these models. So then in the next section, talking about constrained optimization and Lagrange multipliers. I heard conversation earlier about like how to pronounce things. So this is one of these things that I hope I'm saying correctly, but correct me if I'm not. So what this section was talking about is if you have certain constraints on your system that you're trying to optimize. So it can't be above a certain value or it can't be below a certain value. You have certain constraints on all of your different variables, and that can significantly change the space that you're working in. So one of the things that they talked about is you could basically say, okay, anything outside of that range, just give it infinite loss. And so your optimization is going to be heavily, heavily penalized. But then if everything outside of the range is just infinite, then it's not going to have much signal of where to actually go. And so one of the techniques that they introduced was using Lagrange multipliers, which is essentially my kind of simplification of it is taking your constraints and then kind of transforming it into your original variable so that it's part of the optimization itself. So there's a couple of videos I linked in there that will cover it better than I can with lots of visualizations and stuff. So the idea here is we have our original set of variables, the primal variables that we'll call x, and then you have the dual variables that we will call lambda. And so the idea here is that the initial equation, we're trying to minimize this function. So this is our loss function saying how good are we doing? And then we have various constraints. So imagine, I think I have a plot somewhere. Yeah, so imagine something like this, where you have a bunch of lines constraining what the values can be. And so you can do the technique I was talking about where everything outside of that range is just infinity, but that doesn't necessarily help you. And so the idea here is that you transform it to this new set. And then in this set, you're trying to maximize, and then you're saying that the lambda has to be greater than 0. And so this is a slightly different problem that you can actually optimize now. Whereas if you just set everything outside of the range to infinity, you can't really traverse that space any better. So then the next section, looking at convex optimization. So I've always thought of convex as like, okay, I just have this bowl and then I'm going to the bottom of the bowl. But one of the things that they talked about was that when you have a convex set, it's basically saying that between any 2 points in the set, it doesn't go out of the set, essentially. So like, for example, here, if you pick any 2 points in here and then you go find the midpoint of that, it's going to still be inside of this set. And so you can see with something that's non-convex like this, you could put a point here and a point there, and then you say, what's the midpoint? Oh, it's actually outside of this set. So I hadn't really thought of it in those terms before. So it was kind of illustrative to look at that diagram and say, okay, how is this not true? One of the things that they were talking about was strong duality. So that is when the solution for the dual problem or for the primal problem is the same as the dual problem. So like I was saying before, you have the transform set, you can have the same solution in both. That means you have strong duality. And so one of the things that they talked about is you can check if it's convex. You take the first derivative, take the second derivative, and then this is the constraint that I was talking about, where it's saying you pick any 2 points in this set, and then you check if it lands inside of it. And then they also talk about the Jensen's inequality, saying that that is a certain form of non-negative weighted sums of convex functions. I didn't entirely understand the significance of that in terms of the machine learning, but that was something they pointed out. So in the next section, they were talking about linear programming. And so this is like in the diagram here, imagine you have what you're really trying to find is the minimum that's shown by these contour lines. So you have some function that's saying, okay, move in this direction, but then you are constrained in various different ways. So you have all of these constraints here. So it's basically saying you have a line here and it can't go above a certain value. You have a line here, it can't go below a certain value. And then it kind of constrains you into this box. And so this is a slightly different problem, because if you were just looking at these contour lines here, you'd say, okay, just go in this direction and just keep going. You'll eventually find a minimum, or you'll just go into infinity. Maybe it just keeps going down, 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 down. But the constraints here we can see kind of box us in, and so we have this new problem where we can't solve it in exactly the same way. So within these constraints, we need to find a way in order to find the minimum point, which is actually over here. So one of the things I found when I was reading through this is there's like alternate methods, and one of them that I was thinking of, like, is if you just assume that this is always going to be one of the extreme values, what you can actually do is you just basically trace along the outside, and then you say, what's the minimum value? And so when I was learning that, that's apparently called the simplex method. So just a random thing that I came across, I was kind of thinking, okay, well, I could just trace along this. That's probably pretty easy, and that's like a known method.
What's the term for that? It's not fence posting?
What I saw was simplex method. Yeah. Um, and so beyond that, we can look at quadratic programming, and this is similar, but it's saying, okay, now we don't have exactly the same kind of constraints. They're quadratic instead of linear. We're operating inside of a quadratic space. And so this is what this one looks like. So imagine now we have one of these bowl setups and we have our contour lines again, and we're saying that the actual minimum is this point here, but again, we have constraints. And so we look over here and it's basically saying, okay, it has to be within -1, +1, +1, -1 for all of these different variables. And so now we're trying to find the minimum within this box, essentially. So similar idea to the linear programming, but now we're operating in a quadratic space. That's the idea there. So this is the section where I was researching it and trying to understand, but I don't know that I fully get it. So one of the things that they were saying with this section was basically you can take these convex sets and you can describe them with essentially the gradient and some intercept. So you know that it's going to change in a certain way, and you know that the intercept is going to change in various ways, and you can get a full description of this with that with all of the supporting hyperplanes that you get from that. So you have the gradients and you have the C that's adjusting as you're moving through the points. And so in theory, that transformation should maintain all of the information. I don't know that I really have that deep of understanding of it, so I can't describe it any further than that. So one of the things in the Slack, I saw there was some conversation about that. So there's extra resources if you're interested in them over here. So if anyone wants to dig into that topic further, there's plenty of content here.
I have a
Yeah.
really quick question. Just regarding constraints, I'm kind of curious if this is like an example of, like a constrained space. Like I think, there's been a couple times we've discussed, chess playing games and stuff like that. Well, like if you have like two chess bots playing each other, and they're like super trained, etc., then they're always going to draw because they start with like the Berlin end game, and then they like, do a very particular set of things every time because it's like the most optimal strategy. So they set the first opening to be like a known book opening so that they can actually like, play the game without drawing every time. Is that like an example of a constrained space? Like first move is always this particular configuration?
I think you could think about it in that way, but I think it's slightly different context. Like that is a constraint on this system, but I don't think it's a constraint on some optimization that you're doing necessarily.
Yeah, so like a very simple natural constraint is, let's say you have a problem where you're doing some kind of traveling salesman kind of a thing, right? You have a truck and it needs to stop by and do all these deliveries, right? So then basically you're going to constrain that the number of times you go to house X must be greater than or equal to 1. And then you're also going to constrain that it must be less than or equal to 1. in a separate thing because you want to visit each house exactly once, right? If you had a stock portfolio, you're going to constrain that the number of shares you own is greater than or equal to 0. You can't have negative shares. So a lot of problems that just have very natural things where you can't say like, oh, somehow I can maximize this by having like, you know, my grocery store, I have coupons, so I'll have somehow like negative number of tomatoes, but positive cucumber, you know, they're just oftentimes very natural constraints.
For the stock example, we can short a stock.
But there's probably typically a limit of like how much you want to let the bot play around with, you know, like maybe like the minimum that it thinks is like, you know, sell everything or buy everything I possibly can. And you know, you don't want to let it do that because, you know.
Yeah, and to the example where you're shorting stock, probably the financials are slightly different. So you actually want to have a separate variable for how many shares you short, and that is still constrained to be greater than or equal to 0 and has a separate return from the number of shares you outright buy, right? So it's still just very naturally you have, you know, real world constraints where you're going to have to say something has to be below or above a certain something.
I think there's definitely areas where you're doing optimization on physical things and there's clear constraints, but thinking in machine learning context, like we don't typically have a constraint on our weights, for example. We're not saying it has to be between 3 and 5 or something like that. So this is a little bit outside of the optimization that we would typically do in machine learning, I would say, but there's plenty of like whole optimization engines that are just designed for those kinds of things. Like I've seen a bunch of software vendors that their whole thing is just optimization, and they focus on continuous optimization, integer programming, all of these things that are a little bit outside of the like machine learning, deep learning realm, but that's this kind of optimization kind of extended.
Cool.
Yeah. All right. And that's all I have in terms of slides. Are there any more questions? Yeah, go for it.
We're still working on the chapter, right? That was just the third section of the chapter, right? Or this.
That was the whole chapter.
Really?
Yeah.
Cause I feel like I got that far and I didn't realize how close I was to the end.
Yeah.
So I was trying to like really get through it, you know, but I can only take it in like little bit sizes because it's like so conceptually heavy. So I'm happy to hear I'm close to it.
Yeah, you basically made it.
Thank you.
Support vector machine is a good example of this
Hold on one second.
optimization.
Question
Sorry.
online.
It's Hakan. I
I'm
was
sorry, could you
going to
repeat
give
the
an
question?
example about this optimization we are using with the constraints. So the support vector machine that we are using, it applies this Lagrangian optimization, Lagrangian technique to find the hyperplanes that maximize the distance between clusters. That's one example.
Yes, thanks for sharing the examples. So support vector machines do use this Lagrangian duality, and that's coming up in 2 or 3 chapters. And so I think that's specifically one of the reasons why it's covered in this chapter is because we're going to need it when we get to support vector machines. Awesome. I was just going to throw out that probably with neural networks, the most common optimizer we use is Atom instead of vanilla batch stochastic gradient descent. And simplistically, Atom is SGD. It does have momentum, and it has the preconditioning thing that Ryan showed on the slide. And basically, if you had the Hessian, the second derivative matrix, that would give you a really good sense of the curvature in every direction. And we talked earlier about maybe you could explore moving in a couple different directions. The Hessian is incredibly expensive to calculate. So if you're familiar with Newton's method, it's used in low dimensional problems, but it uses that second derivative and it's extremely expensive in high dimensions. So rather than using the exact Hessian, and then on the slide it said like P inverse, because basically what you're doing is you're using the inverse of the Hessian. Actually, I don't know if it's the Hessian or the inverse of it, but either way, it's really expensive. What you want to do is you want to take like high slope things and flatten them so that everything is sort of uniform curvature in all directions. So if you think about a spherical bowl instead of a long skinny valley is what you want. Anyway, so what you need in these various techniques like Adam is you need a rough estimate of what you think that curvature is. And so it would work better if you use the exact Hessian. But since it's so expensive, they use something. So that's why there's every year you'll see there's papers proposing some variation on Adam, because we know that Adam is not the perfect inverse Hessian. And so somebody say, well, what if I do this approximation? Does it converge a little bit faster than Adam? But that's basically what it's doing is a form of saying, oh, you're really steep in this direction, you're really shallow in that direction, let's even them out. And again, it's so that you don't have this zigzag the steepest descent, if you have just a two-dimensional valley, is towards the valley floor. And so you end up zigzagging back and forth across that. What you really logically want to do is to travel along the bottom of the valley in whatever direction is downhill for the valley. But that's not, the gradient never points in that direction. It's always pointing sideways. And so the goal of Adam is basically to change that into a bowl, and then you can go more straight towards your final destination.
Is there a specific term for turning it into a topology problem that way?
I think preconditioning is really the term that's used the most, and again, it's just dealing with the scaling problem. And again, you could imagine in tabular data, we talk about scaling your inputs or whatever, right? But this is something where in one region, the scale could be one way, and in a different region, the scale could be different. So Adam is doing the scaling dynamically. It's not just a one-time saying, oh, age is a really large number and gender is a very small number. It's not doing it globally. It's doing it locally based on what the contour it sees locally.
One thing I wanted to add, just in reference to the learning rate and the gradient. So one of the things about this is, well, you think, why don't we just take the full step? Why don't we just go 1.0 all the way to what we're really doing is when we're taking the gradient, we're saying like find the tangent at this certain point. And if we take the full step, we're saying go all the way there, basically. But this is just sort of an approximation at this local point. It's not capturing that this is a curved line. So if this is saying like we're here and then we want to go all the way there, we can try to extend all the way to the bottom, but actually this curve is changing. So you're not actually capturing the full relationship. And so that's something where the second order and beyond gives you a lot of information about like, oh, actually, I know I want to go here, but it's going to be changing like this. So if you just take the full step, you're actually going to end up somewhere kind of random. You're not ending up like actually where the number needs to be.
So in regards to the description you just gave, you're saying like, and what Ted said as well, calculating more derivatives gives you more information. In fact, too much information, perhaps.
Well,
Expensive calculator.
It's expensive because it's a lot of information.
Each of the individual calculations for each point is relatively expensive to compute. So if you're computing all the points, you're going to n to the n or infinite compute that you're required to do it. Whereas if you're approximating in small steps, you're less likely to leave the space that the graph actually occupies. I think.
It's like you're getting one square.
Yeah, I mean, like, if you imagine like a really kind of like a smaller example, if you have a very small batch size and say you have like a problem like a label for each sentence and whether or not the sentence is, I don't know, like non-compliant or like rude or whatever, like some sort of like analysis of the sentiment, right? You have 1 or 0 next to each one of these sentences, and you have like 10 sentences. So you want the loss is like how well your predictions match those binary values that you get, right? And so to calculate the gradient, you take the derivative of the whole model and the optimization function, all that. And so if you go in a particular direction for like those 10 sentences, do you have enough information to guess on 10 more sentences? Probably not, because you haven't, the model has not seen like most of the cases that exist. It probably, I mean, to the extent any model has like knowledge of, you know, it doesn't have a good model of what is like, you know, rude or good or whatever. But if you throw a whole bunch of data at it, if you were to like overfit a model on just those 10 sentences and you were able to predict those 10 sentences again, then it can be said you might have a good statistical model of that relationship, but it's just not like the gradient has not been determined yet because you only have 10 sentences. Whereas if you take another 10 sentences, it might be pointing in a different direction, you know, to update the parameters somewhere else. And so, you know, the point is you move through batch by batch and you try and figure out what it's actually modeled. So.
Right, because when you guys are saying all that, to me, it sounds kind of like an analogy would be like pouring a waterfall, and so you're holding a cup up to a waterfall. You know what I mean? It's just like too much information to process it. So like theoretically, if the brain processing it was more powerful, could you simply make all those calculations, or would you still have the same problem?
It's if you have an infinite number of monkeys, they will immediately produce the works of Shakespeare.
Oh, really?
Well,
That's
because
the objection.
well, no, it's
So pulling this back to the conversation, from what I'm hearing, I don't think my mental model matches yours, okay? It's not a question of information is bad. It's just a question of how much does it cost you to calculate that information, okay? So if you have an LLM that has 100 million parameters, okay, and I calculate the Hessian, and it's a 100 million by 100 million square matrix, and I ask you to invert that matrix so that I can condition things, that's a n cubed problem naively on a 100 million by 100 million matrix. It's going to be ridiculously expensive to calculate that. You probably could have taken, you know, right, like millions of gradient steps in the time it took me to calculate that one second derivative or inverse of it. So it's really not a question of whether the information is good or bad. Newton's method is one of the methods that uses the second derivative, and it works better than vanilla gradient descent. The question is just, is it more expensive to use the second derivative, or is it cheaper to just take multiple steps using only the first derivative? It's a pure question of speed. In terms of convergence properties, I think mathematicians could say second order methods are always better than first order methods. Doesn't mean in terms of wall clock, how long it takes an NVIDIA GPU to do those steps, that it will be faster. But in terms of number of steps, I think you're basically always better with a second order method. So it's not that information is bad. It's just whether or not it's expensive or cheap.
Okay, so then may I ask what the definition of cost is in the context of, I guess, what we're discussing right now?
the computation on a chip. So an NVIDIA GPU will have 10,000 CUDA units. So if you want to do 10,000 operations on 10,000, if you want to do one operation on each of 10,000 different things as a vector, you can say, hey, take this 10,000 long vector, do this calculation on all of them, and that'll cost you essentially 1 unit of time.
Oh.
So you can make 10,000 guesses essentially, to trial and error and see, hey, is this better? Versus one really expensive calculation where it has to go through this step, then this step, then this step, then this step.
Yeah, it's a fair question. I mean, it could turn out that one algorithm runs faster on a Mac with its, GPU, and a different algorithm runs slightly faster on an NVIDIA GPU. And if you're CPU only, then there's a third algorithm that runs slightly faster. So it's a fair question, but by and large, if you just look at like the number of multiplies, the number of flops, that's like a pretty good approximation for what's going to be faster in general.
And to finish off the hardware thing, if you want to look up NNX, the original Intel multimedia extension for that, that's the simplest way to look at what the hardware stuff is doing.
Okay, cool.
NNX.
And then that's not the index. That's not good.
I want to mention one thing. So,
I have a question to be
Uh,
honest.
can you hold on a second? I'm trying to, the hybrid dynamics are not great. Yes.
yeah.
Let
So,
me,
Hakan, so I want to
hold on
mention
one
one
second.
thing.
Hold on. Sorry, Hakan. Let me just
Sure.
put you on speaker here. All right, let's try this. Go ahead.
Yeah. No, I cannot hear you.
Yeah, go ahead, Hakan.
Oh yeah, okay. So I wanted to mention that so these convex optimization they are limited because, as you mentioned, these neural networks and then other machine learning models they have to calculate this huge matrix input feature matrix inverse, and then that's usually infeasible. And so that's the first thing, and that's why this neural networks, they are usually using very simple functions, so that, and then the derivative of it is very simple, right? And but there's also another implementation of this optimization. I think it's not mentioned yet. So the hyperparameter tuning, and then that's where we use really other non-convex optimization techniques with the constraints, right? Like Bayesian optimization, genetic algorithms. I don't know if you can hear me, but yeah.
Yeah, you talked about. All right, sorry, we got the beginning, and then we lost your audio when you were talking about neural networks with simple functions. So
Oh
you
yeah.
want to try again on that part?
Sure. So the main thing that I wanted to mention is like the book. I think I didn't see that, but there is also non-convex optimization techniques, mainly and mostly we use for hyperparameter tuning, right? And those methods they don't really consider much about the gradient, and then the inverse of function. We don't do that in that methods. And also the beauty of it is you can put constraints on those. You can define upper bound for lower bound for the spaces that on the search space. So there is also that implementation, and we didn't mention, or I missed it. So I wanted to highlight that.
Yeah, that's a great point. I think this book was published a decent while ago, but we do have like genetic algorithms and a bunch of other things that don't require gradients in order to do optimization. Thanks.
You guys can clarify that in the Lagrange stuff. I thought that was what, who was it, like the way what he was describing, it sounded like with the Lagrange stuff, there's the fx plus lambda di of x. I thought that was how they're preconditioning the space for like change. You can put the lower bound is f of x and the upper bound is like lambda g of x, something like that. Did I misunderstand the whole point of the Lagrange stuff?
So the Lagrange stuff was in terms of the constraint. So that's saying like how do we encode this box into the thing that we're trying to optimize? That's a little bit different from what Hakan was saying.
Okay.
Cool. Any other questions?
If no one else says that it comes on this, that's something for the probability stuff.
From last
All right, let's just see if we have anything else here. Yeah?
I have one question. I was something I've been thinking about that. I was reading that you use these, you can train these large language models, and then you can distill the model into a smaller model and get similar performance. And I was wondering what, if anyone had any ideas about what the link is between the way we're optimizing these models that we need to first train the big one. Afterwards, we can then scale the model down in size and get similar performance. And do you have something like what the properties of or how the optimization feeds into this?
I think that ultimately the bigger models must make the optimization easier in some way. So you have a bigger model, it changes the space in some way so that we're able to find a better final value. And then you can take that to the smaller model and say basically jam this one into the other one, and it's better because the larger one is actually giving it better information to operate off of, versus the smaller one has a more complex space that it has to go traverse by itself. So that's my connection between the two of them. How exactly that works, why it's not, you can't just say why doesn't it just get the same weights as the larger one on its own? That's a little bit unclear.
Yeah. So one of the, we don't have like the solution, but one of the properties we know about what you're talking about, why is it that a big neural network can train and the small one doesn't train as well on the same exact data, is that current neural networks, the way we design them, require sparsity. Okay. So you can show that CNNs, LLMs, all these very large neural networks, if you train them and then you do a little bit of search, you can delete something like 80-90% of all of the parameters, and you'll only lose maybe like 1% of performance. Okay, so we know that these weights are highly sparse, that we built this giant thing and we didn't really need all of them. All right, so what if you just had fewer and then it doesn't work? So we know that there's this sparsity that's required. What we don't know is exactly why, and of course, lots of people are trying to do research to figure out if they can't. But it seems that for what you were talking about if you try to distill knowledge from a larger model to a smaller model, that there are techniques that seem to work slightly better than vanilla supervised training, supervised learning. And distillation is one of them that seems to work slightly better, which means that you can get more out of a certain amount of training data and that your parameters can be more dense. They don't need to be. A simple technique you can do is you can build a really large neural network and you can test the parameters to see whether they're important, and you can remove all the ones that aren't. The problem is, I don't know what the term is exactly, but unstructured sparsity isn't any faster to compute on an NVIDIA GPU than a dense matrix. Okay, so if we delete a whole bunch of stuff and it doesn't run any faster, there's not like a super strong motive to do it. There are companies like Neural Magic is the one that comes to mind, where they run stuff on CPU and then they don't care because they're not doing parallelized operations. And so then if you get rid of 90% of the stuff, you're actually doing 10% fewer matrix. I mean, you're only doing 10% as many matrix multiplies. And so for them, they do take advantage of unstructured sparsity. So there's been a whole bunch of research, I'm not the expert on most of it, where people say like, what if I force a certain structured sparsity while you're training so that when I prune it, I can actually get like block, density, and then take advantage of the blocks to do relatively fast matrix multiplies. Not quite perfect, but better than just But if you just have individual single random zeros in your giant weight matrices, it doesn't speed things up great. So
That makes sense.
yeah.
Matrix is the same size.
Yeah. So there's one set of papers that I'm familiar with that talked about mode connectivity. And so the idea is that when I think of local minimum, I think of like the surface of the moon. You have big craters and you have little craters, and sometimes you have little craters within big craters and nested, various levels, right? And so there's no way to really know, is there some really deep, shallow crater in one spot unless you like investigate each one. Okay. Now for the moon, maybe it's true that most craters are sort of shallow. They don't like, they're not deep and pointy, but you get the gist, right? So like you really just don't know if just over the horizon there's a really deep crater. There's no way to know. It's not predictable.
Yeah.
Right? Um and so there's this hypothesis that in high enough dimensions, that's not what it looks like. What it looks a little bit more like is when we were talking about like a mountain range and there's valleys and all the valleys are connected. Okay. Now, the problem if you're using that just three-dimensional analogy is that once you get to if there's a certain valley that has a low point in the middle, then you're just going to get stuck in that. Okay. And you're not going to make it to the next valley that might be lower. But there's this one hypothesis that if you were in high enough dimensions, okay, so if you have 100,000 free dimensions to go, at least one of them will be straight downhill and won't have a dip in the middle. And so then if you have, 10,000 different dimensions in which to get to the next valley, one of them will be downhill and will let monotonically downhill, so to speak, and let you get to the next valley. And then from that valley, there will be a direction that's almost monotonically downhill that'll let you get to another, until eventually you get to one of the many valleys that are very close to the global minimum, maybe not exactly the same, but so that's this one hypothesis that you give it enough extra dimensions, but that's why you wind up with all this sparsity is because you've blown up the dimensionality so much just to give it those degrees of freedom. So it's a little bit like knot theory. If you add a bunch of dimensions, you can like untie any knot. And so maybe it's something like that.
Reiterate that, or recap that. So what you're saying is, and this is just a hypothesis, but like, the larger language, or the large language model, because it has so many different extra, independent dimensions, it can more accurately like calculate the most optimal direction of gradient descent. And that could be what is assisting the smaller model to converge in that direction because it is inferring that during the distillation process. But if like the smaller model was just being trained on the raw data, the gradient wouldn't necessarily be as clear.
So both the large and small language models are all sparse. They all have tons of wasted weights. But when you do supervised learning, oftentimes you give it like a 1 and a whole bunch of zeros. When you do Hinton style distillation, if you have a vocabulary of 30,000, you're giving it 30,000 floating point numbers between 0 and 1. It is a much different signal, and that type of training seems to not require as much sparsity as just giving it a 1 and a 0 kind of a signal.
It sounds like that might be because you're just working in a much higher dimensional space, but means that you're just more likely, according to this hypothesis, to have a direction going. Like if you're trying to find the coldest spot in a room, you're on the floor, you can only go up the floor, you can go up and down.
Yeah, and in this case, like with a vocabulary size 30,000, you're getting 30,000 feedback signals. So maybe one of them you're stuck and you can't move downhill, but at least maybe one of the other 29,000 signals you're getting has a direction downhill. And once you move there, then you'll be able to continue to move in other directions. So like you mentioned MCMC, right? So if you're doing like coordinate descent, right? Maybe right now I'm only improving in a certain direction, but then later on in that next valley, I can improve some other aspect of it, right? So now I'm getting plural agreement, right? And later on I can get tense agreement, and later on I can get, other parts of language. But I'm in a local minimum right now where I don't see any benefit to changing my verb tense, you know. So maybe that's why, but I don't know. I'm not super well read, but but for sure the sparsity is a thing that people know absolutely for sure, is that any decently large, I mean, we're talking like millions of parameters, will be highly sparse, and that most of the value is contained in a relatively small percent of the parameters. Thanks for the question. You've been very patient. Did you want to add a comment?
Yeah, it'll actually tie into things at this point. So another way to look at the large version of the model versus the small parameters is you have a bitmap image and you have a JPEG. If you look at the bitmap, you have more data points. So if there is one pixel that's off in the original, that's not going to show up in the JPEG as you compress it and say, hey, that's not an important signal. So the larger parameter one will be able to recognize, oh, that case also exists. So you can think of that as a local minimum that you get stuck in one way, or a way getting stuck in one. And that's how that all compresses out. And that also addresses I think it's not so much the dimensionality of it, why the larger parameter model is more accurate, but because it just has more data points that it works with. So if there is an edge case, it's more likely to have retained that edge case exists and be able to address it.
Yeah, I think we have to be careful with those kinds of analogies because like if you train it on the same training set, the loss function, that surface is identical for both the small and the large model is to a certain degree. It's just the ability of our gradient descent optimization method to find a really good local minimum. And that's still an unsolved mystery, is why does gradient descent work so well? I think you can easily come up with a pathological example of some mathematical function that has the same number of variables as, like, say, MNIST. And gradient descent will not find a good solution at all. So it's certainly true that not all functions can be optimized as well as neural network gradient descent. And so people for a long time have been researching, is it that the way we build neural networks, they have really good loss functions? Is that what's going on? Or is it that gradient descent is so freaking awesome? And I think they've ruled out that gradient descent is so awesome. So they're saying it's something about the design of neural networks, and if we did neural networks differently, then maybe they would stink. So the question is, how do we know if we've explored enough of the space to find a good global minimum? My understanding is today in deep learning, we have absolutely no idea. We just do a training run. And if that's all you have compute budget for, you cross your fingers and hope it's really good. If it's a smaller problem, you can do 5 repetitions of it. And if they have very similar metrics, then you're like, yeah, this is probably solid. But as far as I know, there is nothing. It's one of the reasons why I have this favorite paper from about 2 years ago that basically said, if you take a small model, you do a whole bunch of hyperparameter tuning, and you can afford, because it's small, to do a bunch of repetitions to see that, like, this gives me, then these same hyperparameters will work if you scale up, like learning rate and momentum. These hyperparameters will work if you scale up the problem bigger. But you have to scale it in this way. You can't just arbitrarily say, let me add layers, let me whatever. I thought it was this really awesome paper because of exactly what you're bringing up. It gives you some guarantees, and I don't know, and it seems to me it just hasn't really become that popular as I thought it was going to be.
I want to add to that.
Yeah, we hear you.
Yeah, so that what you said is exactly true because the solution space is huge. So it's impossible to say what would the local minimum is the best local minimum or the global minimum. So there are techniques to help with that. So the one they call it, I forgot it. So you adjust the learning rate or the parameters over time based like energy based kind of idea or like how they use in simulated annealing. So you lower the temperature or you lower the learning rate in time. So you allow model to explore more the surface solution space, right? So and towards the end of the iterations you give more weights to exploration of the local minima you found. Does it make sense? You start with first you start with exploration and then you turn to exploitation.
Yep, that's cool. I mean, every year there's more papers that say, let's try doing this tweak of gradient descent. So, yeah.
Yeah, the word I was looking for, sorry, it's scheduling. So they schedule the learning rate.
Yeah. Yeah. So if you're familiar with Fast AI and what's his name, Jeremy Howard, he's a huge fan that you shouldn't just start with a high learning rate and go down, that you should go down and then back up and then down and back up a couple times, that you should do this cyclic pattern. I think that was primarily for computer vision, but I know that he was massive proponent of this annealing process where you cycle up a couple times. It's very common to see people not do that though, and just use something similar to cosine where it starts high and it gradually gets smaller at the end.
But I found some research regarding redundancy in data. And people, some researchers just randomly take out some percent of the data, starting from 5% and ending up 80%. And for each of the kind of split, they trained very similar models, but with like lower number of learning layers or hidden states, just to wait like to adapt this model for this amount of data. And they found actually not a big decrease in performance. They found very slight decrease in performance, which actually means that probably there are a lot of redundant data, like I mean training data for large language models, and if we can have maybe a more wiser way to understand the data on which we train the model, maybe we can use just smaller model for that.
That's awesome. I hope you guys were able to hear the comment. I know sometimes people farther away, it was related to not just redundancy in parameters, but redundancy in data. So I think there's a lot of research with LLMs in terms of getting high quality, smaller but high quality data sets. I know that at my work, we're doing some computer vision models, and basically we're fortunate enough that we have a lot of data, but it'd be very expensive to train our model on millions of images. And so we'd rather actually have a really good smaller set and be faster to train. So TBD how that works out, but that's one of the things that we're working on.
Last week there was a paper or something on compressed arc, what was basically trying to say, hey, LLMs are trying to be generative intelligence, but if you can compress data perfectly, that also demonstrates generative intelligence. And then there's a paper by Mahone in 2006, basically advocating for compressing large amounts of text to be predictive. In English, the entropy for data is essentially 1 bit per character. PKZip doesn't do that. All that stuff doesn't do it. But that paper was very accessible, and it talks about some of the probability stuff.
Cool. And again, I hope you guys could hear that, but talking about how compression is the the degree of compression is a good sort of metric for your level of understanding. So if you could compress text really far down to like a bit per character, then you probably have a really good language model. Thanks.
Yeah, yeah. So either one of those things.
All possible values.
Yeah.
Yep, still a lot of research with getting the right data, the right models. All right, we have a hand raised. Faye? You're unmuted in Zoom, but I don't hear you. I don't know if it's your microphone.
Hello.
Yep, now we hear you. Go ahead. Oh, wait, now you're muted in Zoom.
Hit M.
Hello. Can you hear
Okay,
me?
go ahead, Faye. We hear you now. Did you want to ask a question, Faye? We hear you. All right. Sorry, we're not getting your audio. All right, any last questions?
I'll go one thing. So just related to the point a second ago about like there's this kind of general idea of data distillation. So like you were mentioning, like you can filter and select like these are the best data points to go train against, and that gets you most of the accuracy. There's this Google paper from a while ago that was essentially saying we can do even better than that, basically saying generate examples that teach the model the best possible in a very condensed way. So if you could say, I had 10,000 images, now pick the 1,000 that's most instructive or something like that, that's useful. But they were able to go all the way down to 10 images for MNIST, where they basically said, okay, compress all of the knowledge that we can into 10 training examples. And it's not even digits anymore. It's basically just, here's the pattern that makes up a 4 or a 9 or whatever. And so they only trained on these 10 images and they were able to get accuracy of 97%, which is pretty crazy. But the downside of that is you still had to do something in order to look at all of the data and then create these samples. And so it's an interesting trick, but how useful is it? I don't know, but it's an interesting area.
That's cool. All right, thanks everyone for joining us. We will have the next book club chapter in 2 weeks. And then just a reminder, next week we're going to do case studies. And in 3 weeks, we will have a social event instead of a technical event on March 29th. All right, bye everyone.